Now that you're familiar with the general idea of an improper integral, let's generalize a little bit. Let's look at the integral from 1 to infinity of x to the p power. So I want to split this up into two cases, when p is equal to -1 and when p is not equal to -1. So remember one of the examples before, when p is equal to -1, we're looking at the integral from 1 to infinity of 1 over x dx. And we learned that that diverged. So we want to consider the other cases when p is not equal to -1. So I've split this up into almost a piecewise function when I'm looking at this integral. So x to the p, what is the antiderivative of x to the p power? Well, that's going to be 1 over p plus 1 times p to the, times x to the p plus 1 power. Alright, so I just combine that into a single fraction, and that's what I have written here. Now, when p is equal to -1, then the antiderivative is just the natural log of x. And we've worked that one out already. So I want to evaluate each of these from 1 to a. So you might want to hit pause for a minute and take a look and make sure you understand exactly where I got these two pieces. Okay, so now when I evaluate each of these from 1 to a, I'm plugging in I'm plugging in this a value for x. The a value for x. And then I'm also plugging in the 1 for the x. And so when I do that, I get what I have down here. So we have the limit as a goes to infinity of a to the p plus 1 minus 1 to the p plus 1 and 1 to the p plus 1. Let's do this in a different color. That simply is going to equal 1. So that'll simplify just to a to the p plus 1 power minus 1 all over p plus 1. And remember, this is when p is not equal to -1. And then for the other one, we're going to have the natural log of a minus the natural log of 1. And we know the natural log of 1 is just equal to 0. So if I simplify this yet further, here's where we're at. Okay. Now, we've already talked about this second case here. As a goes to infinity, the natural log of a also goes to infinity. But the more interesting case is this one, when p is not equal to -1. What do we get for this expression here? What's the limit as a goes to infinity? So remember, the p-value is fixed, so you take one predetermined p-value, then you can look at the limit as a goes to infinity for that p-value. So we actually have to split this into further cases. So what if p is, let's say, greater than, let's split this up, I'll use blue. What if p is greater than -1? So for example, if p is 0, or 1, or 2, or 3, or even 1/2. In that case, when p is greater than -1, this exponent up here is going to be positive. And so we're taking the limit as a goes to infinity. So we're taking bigger and bigger numbers, a, raised to a positive power. Well, that's just getting bigger and bigger and bigger and bigger. And then subtracting 1 from that doesn't really affect it very much. And then dividing by p plus 1, it's still, we're getting larger and larger and larger values. So when p is greater than -1, this limit is going to be going to infinity. But what happens in the other case? What if p is less than -1? Like -2, or -3, or -4. What happens in that case? Well, when we look at this exponent, if p is less than -1, let's just say -2, then we're raising a, which is getting bigger and bigger and bigger, we're raising that to a negative power. So that's actually giving us a fraction that's getting smaller and smaller and smaller and closer to 0. and then we have minus 1, and then all over p plus 1. So what's happening in these two cases is we're going to get either infinity when p is greater than negative 1, or we're going to get the fraction negative 1 over p plus 1 if p is less than negative 1. And then the second case, and that's when p was equal to negative 1, we had infinity. So you can see that 2 out of these 3 situations we're going to get infinity. There's only one situation where we're actually going to get some finite number, some answer for this problem. So it's only going to converge when p is less than negative 1. Let's go back up to the top, because we've talked about a lot of stuff here. So what we're doing is we're looking at this. And so when p is less than negative 1, it'll converge. But in all other cases, it's going to diverge. So I've summarized that. Our integral from 1 to infinity of x to the p dx will converge only if p is less than negative 1. Now another way of thinking about this, instead of thinking of it as x to the p power, we could think of it as 1 over x to the p power, and in that case, it'll converge only if p is greater than positive 1. So you'll see some books will show it in this form, and then other books will show it in that form. And as you get into studying power series and Maclaurin and Taylor series, this is probably the form you'll see more often. So that's the one that I'll talk about in our examples. So when we're doing an integral from 1 to infinity of 1 over x to the p, it'll converge only if p is greater than 1. So that would mean, for example, just to have you think about this, that means if we do the integral from 1 to infinity of 1 over x squared, that's going to converge, because in this case p is 2, and that's greater than 1. Or if we do, let's say, from 1 to infinity of 1 over, how about x to the 3 halves? P is 3 halves here, that's still greater than 1. How about the integral from 1 to infinity of 1 over x to the 1.0001? That'll still converge because p is greater than 1. Alright, so let's look at a couple examples. One of the things that we may run into a problem with is if you have trouble anti-differentiating when you're trying to solve an improper integral. So it might be useful if you can compare the function that you're trying to find the antiderivative of with another function, and you already know if that other function converges or diverges. So let's say we have a function f, and it's always less than or equal to g of x, and both of these functions are positive. They're greater than or equal to 0. I should say non-negative. And this is for all x that are greater than or equal to a, because a is where we're starting our integral. Then, if we're trying to calculate the integral from a to infinity of f, if the integral from a to infinity of g converges, and g is always greater than or equal to f, then that means that the integral from a to infinity of f also must converge. Think visually about what that's saying. Picture a graph, and I don't know, g is up here, and f is up here, and let's say a is right here, and we're going from a to infinity. So we're trying to figure out this. Well, if we know that the area under g is a finite amount, or it converges, then certainly the area under f is also going to converge. So that's basically what this first statement is saying. All right, let's think of the opposite case. If the integral from a to infinity of g of x diverges, or I'm sorry, it'll diverge if the integral from a to infinity of f diverges. So what that's saying, you can use the same picture, and it's saying if the area under f diverges, say right here, if that integral from a to infinity of f diverges, and if g is greater than f, then certainly the area from a to infinity for g is also going to diverge. So if you keep a picture in mind with these statements, I think it should make a lot of sense for you. Alright, so let's try an example then. Show that the integral from 0 to infinity is convergent. So the claim is that that area from 0 to infinity under that curve, whatever it looks like, which we probably don't know just at first glance, we want to prove that that equals some finite number. So there's a hint here which might help you use this comparison test. And the hint is that 1 plus x squared is always going to be greater or equal to x squared for all real numbers. Even if x is negative, because we're squaring it, it becomes positive, and then we're adding 1 to that amount. So how do we want to do this? Then let's look at, so if I want to do the integral from 0 to infinity of the square root of x over 1 plus x squared, I could look at the integral from 0 to infinity of the square root of x over x squared. Now, I can simplify this. It's x to the 1/2 power on top, and it's x to the 2nd power on the bottom. So that actually simplifies to 1 over x to the 3/2 power. And I already know that this one converges to a finite value because it's one of those 1 over p, or 1 over x to the p integrals, and p is equal to 3/2, which is greater than 1. So from what we proved before, since 1 over x to the 3/2 converges, and so let me write this, since, usually you'll write like a couple of sentences explaining the logic behind this. So since the integral from 0 to infinity of the square root of x over x squared converges, and this function, the square root of x over 1 plus x squared, is always less than or equal to the square root of x over x squared. So let's circle this. So this one is like my f, and this one is like my g in that comparison test. Therefore, since g converges, I know that the integral from 0 to infinity of f, which is root x over 1 plus x squared dx, also converges. And at first, this might take a while, a couple times thinking through it to get the hang of this idea. And this is kind of a new concept for some of you when you're trying to decide if something converges or diverges and we're comparing it with another function. So there's a lot going on here. So if at first this seems a little confusing, play back through it a couple times, and I think you'll get a grasp of it. But it might take 2 or 3 times to think through it. Okay. So the basic idea, though, is that to figure this one out, we compare it with one that's similar to it. And the one that's similar to it, we know from that p-test that this one converges because p is greater than 1. Remember, that was the integral from a to infinity of 1 over x to the p. That's a terrible exponent. 1 over x to the p. And we learned that that one will converge when p is greater than 1. And in this case, p is 3/2, which is greater than 1. So that's how I know that this one converges. And since each term of that one is greater than or equal to each term of this one, therefore the integral for the original is also going to converge. Alright, let's look at one other idea to wrap this up. So, if the integral from a to infinity of the absolute value of a function converges, then so does the integral from a to infinity of the function without the absolute value. So I think, if you think about that for a minute and think about the graphs and what they would look like, what happens when you do an absolute value compared to taking that off, this should make a lot of sense visually for you. I'm not going to go ahead and prove that. So, with that in mind, let's show that the integral from 1 to infinity of cosine of x over 1 plus x cubed converges. Alright, so what I'd like to do is use this absolute value idea. So let's look at the integral from 1 to infinity of the absolute value of that same function, cosine x over 1 plus x cubed dx. Now, since we're going from 1 to infinity, 1 plus x cubed is always going to be positive. So I can go ahead and take the absolute value off the denominator, and I'll just keep it in the numerator. One plus x cubed dx. Alright, so what do we know? Well, we do know that the absolute value of cosine of x over 1 plus x cubed, wouldn't you agree that that's always going to be less than or equal to 1 over 1 plus x cubed? Why is that so? Well, doesn't the cosine take on values between negative 1 and 1? So we know that the greatest that the cosine could equal is 1. So therefore, the absolute value of cosine of x over 1 plus x cubed should always be less than or equal to the fraction 1 over 1 plus x cubed. Alright, so where do we go from there? Do you see it yet? So remember, let's go back up to the top here. If I can show that this converges, then so does that. So I need to show that this thing converges, and therefore so will the original from the problem. And they already told us that it's going to. They said show that, so you know that that's true. So this less than or equal to 1 over 1 plus x cubed. How can we show that this integral 1 to infinity of 1 over 1 plus x cubed dx converges? If you can show that that converges, and that's greater than or equal to this one, that would mean that this one converges, and therefore we've gotten what we need. So, what about this 1 over 1 plus x cubed? Well, wouldn't you agree that 1 over 1 plus x cubed is less than or equal to 1 over x cubed? And remember, x is going from 1 to infinity, so x is always positive values. So this first fraction is always going to be a little bit smaller than the second fraction. But wait a minute, the second fraction, we know the integral from 1 to infinity of 1 over x cubed converges because that's the 1 over x to the p, and p is greater than 1. So that one, so if this one converges, so does this one, which is smaller than it by the comparison test. And so if this one converges, then so does the cosine over 1 plus x cubed converge. And therefore, the original from 1 to infinity of cosine of x over 1 plus x cubed will also converge. And I'm not going to spend time writing out a few sentences, but that's the main idea behind that. So using the comparison test, this absolute value idea, and this integral from 1 to infinity of x to the p, or 1 over x to the p, in combination can help you decide if a lot of these integrals are going to converge or diverge. Alright, so I have some problem sets from 2b, which starts on page 55. And once again, if you have questions on any of this, please shoot me an email.